Today I would like to talk about how to implement UNS systems with OPC UA. Specifically, I am going to show how OPC UA over MQTT has the features needed to build a UNS. So let's talk about UNS, otherwise known as Unified Namespace. UNS is a communication architecture for OT environments that makes OT information available via a central broker. These brokers are commercial products that are designed to be scalable and to support local and cloud-based subscribers. This architecture allows for the automated discovery of information available and can adapt to changes in the environment over time. This means changes to the configurations of devices on the factory floor will be detected by UNS consumers who can see the updated information models. This architecture also assumes that OT information is organized using information models that reflect the needs of the business. This can make use of enterprise-wide standards, such as ISA 95, to organize all information into sensible hierarchies. Let's talk about objectives. I will show how OPC UA over MQTT can be used to build UNS applications that can automatically discover all available data and their information models. I will also show how meaningful information models specified at the device level can be used to provide a consistent information model as the data flows through different pathways. And to give you a better idea of what I'm talking about here, let's look at a simplified view of a factory. In this case, it has a single boiler that is controlled by a PLC using GPIO to implement a control loop. This PLC is going to have an engineering tool that defines, among other things, the actual program to implement the control loop. But it also has to define some sort of information model, which is used to describe the different tags that are visible to applications interacting with the PLC. You're also often going to have some sort of local HMI. This can be an industrial control panel. It could be a local SCADA that's connected via the LAN and does not depend on the broker. This local HMI will have access to capabilities that cannot be realistically implemented via a broker based outside the factory. The PLC will also use OPC UA to publish its data to the broker, which makes it available to the UNS consumers. In this demo, I will be introducing a web-based UNS dashboard that is OPC UA aware and is able to automatically discover multiple boilers that are deployed at different enterprise sites. The code to implement this application is available on GitHub. And just to give you a little bit more context in terms of what you're going to be looking at, the publishers that I'll be using for this demonstration are simulators that implement a control loop that adjusts the water level of a boiler. The information model for this boiler will include the various sensor outputs, actuator inputs, and I'd like to get into the actual demonstration of our UNS implementation. What we're looking at is a web application that's running on Azure and is written entirely in JavaScript. All the source code is publicly available in the OPC Foundation GitHub repositories. This application depends on the various metadata topics which are defined by the OPC UA specification. So, at this point in time, there is nothing actually publishing to the broker, but it does remember the fact that there was a couple publishers that used to be online that are not currently online. These come from the status messages which have the retain bit set. Now I'm going to start up one of these publishers and watch the status switch to operational. And as soon as I do that, you'll see the namespace view is populated automatically. We will need to wait a bit as I start the publisher in the background. Once the publisher starts up, a hierarchical structure appears. The yellow folders actually come from the topic hierarchies. So what we're seeing here is a fairly sensible ISA 95 based topic hierarchy that organizes the different boilers that are in the enterprise into sites, cells, and units. Note that the visible topic hierarchies are only used for the data messages. The metadata messages are always sent to predefined topics to allow for auto-discovery. And underneath the actual units, you can see some more detailed information about the physical device on the factory floor. In this case, you have a boiler that has a number of inputs and outputs. If you drill down to the individual tags, you will see that you some additional properties including human readable descriptions, EU ranges, and engineering units. If I browse around a bit, you can see the properties associated with the different tags. Note that the properties come from the metadata messages and are not sent with the actual data. Now, if you select a higher level folder, you can see the live data coming in for all tags beneath it. The web app merges the data and the metadata into a single view, which is why the engineering units appear. One of the philosophies that's built into OPC UA is the separation of the metadata from the data streams. The data streams are designed to be very small, only contain the changes from the last update. The metadata tends to be larger, has descriptive information such as human-readable text. Every data message can be linked back to the associated metadata. Data messages can also have a metadata version, which signals to the subscriber that their metadata may be out of date. The metadata itself is sent to a different topic that has the retain flag set. So as long as a publisher is online, the UNS dashboard will be able to get the metadata and build out the structure, even if the data isn't currently available. In this example, the data messages are going to topics that are meaningful to the enterprise. The UNS dashboard discovers these topics by listening for metadata messages that specify where the data messages are sent. This allows the auto-discovery to happen even though the data topic structure is not known in advance. Now I'm going to start up another instance of a publisher that provides information about boilers installed at another site. It will take a bit as I launch the publisher off screen. Note the code for the sample publisher I am using is also available in the OPC Foundation GitHub. The new publisher was automatically detected, and the hierarchy for the new site appears. Where exactly is the information model with drum and pipe components coming from? Well, as I mentioned in the intro, any real OT system will require that devices be configured with some engineering or configuration tool. This is particularly true for devices like PLCs, which need to have programs uploaded before. The application on the screen is an example of an OPCU, a modeling tool that can be used to create information models. The structure and additional metadata, such as human-readable descriptions, are entered into a tool like this. Notice how the model in the tool looks the same as the model appearing in the UNS dashboard. However, some of the information in the tool does not appear in the UNS dashboard. This is because some information is not needed or has access restrictions that would require it to be hidden or published to different topics that have restricted access. The need to restrict access to some data is where the ability to specify site-specific topics becomes quite useful. For example, let's say a machine installed in a factory provided maintenance information that the machine vendor needed to access. Yet the same vendor should not be given access to data for process information belonging to the factory operator. In OPC UA, a single publisher can publish two different views of the device to two different topics to resolve these kinds of conflicts. Now I'm going to show OPC UA client that connects directly to the publisher using the client-server protocol. In the view in the middle, we see the drum level updating in a set point. I will change the set point and then switch back to the UNS dashboard. While OPC UA actions could be used to change set points from the UNS dashboard, only allowing local applications to access to features that could change the operation of the device has a security benefit. We see on this screen that the set point has updated to 300. Note that the data is being sent to its own topics and small messages that only have changes from the last message. The structure and other context come from the metadata messages. There is a lot of value in a coherent information model that follows the data from the engineering tools to the devices to whatever enterprise applications use it. The examples I presented today used a base model that was factory-specific, but was reused across multiple installations of the same hardware. However, that model incorporates features from common models, such as engineering units. This concludes the demo, and I hope you found it useful. We will be producing more demos to highlight different features of OPC UA over MQTT. One of particular interest will show how actions can be used to control a device from the UNS dashboard. Thank you for taking the time to watch the video, and we welcome your feedback.